So now we understand how to classify our substrates according to steric hindrance. And we can look at our first part of our flowchart. If we have a methyl substrate, well, we're going to have an SN2 reaction. We're not going to have any of these other types. Fantastic. We can already figure out one type of reaction mechanism that we have. But the next thing we need to understand is the solvent type. So you see, these reactions are going to be happening in a solution. And we need to look at what kind of solvent is that solution made of. Often we'll have water, but we might have a solution of methanol or dichloromethane or acetone. So we need to be able to classify those solvents as protic or aprotic. And that is going to have a strong effect on how strong a nucleophile is. Now, we don't know what a nucleophile is yet, and we're going to get there. But before we do, we need to understand protic and aprotic in order to break this flowchart up a little bit more. Now, protic and aprotic, what is this even referring to? Well, the pro in both of these words is referring to protons. And if we remember anything about acid and base chemistry, a lot of it is going to be happening based on the transfer of protons. So when we're working with organic reactions, it's going to be really important what kind of protons, or hydrogen plus, which is H plus, we have floating around. How much of that is there? So a protic solution is going to be one that has a lot of interactions with H plus, which is really going to be looking at hydrogen binding. So if we have a lot of hydrogen binding in a solution, in a solvent, it is a protic solvent. Now, when do we have hydrogen binding? Well, we have it when we have an H to N, an H to O, or an H to F bond. Now, the H to F bond is only going to be hydrofluoric acid, which is so dangerous we would really never use it as a solvent. So we can actually eliminate that. So we're looking for a solvent that's going to have a nitrogen to hydrogen or an oxygen to hydrogen bond. An aprotic solvent is referencing a solvent that doesn't have hydrogen binding. It's still going to, as by definition, a solvent is going to have some polarity in the molecules. That's what allows it to dissolve these things. And so when we're looking at a solvent, we're really looking, does it have hydrogen binding or does it not? So let's look at some examples of each one. A protic solvent could be something like water, which is H2O. H2O, which has a Vesper model like that. Another great example would be NH3, ammonia. An ammonia solution could be our solvent. All right? And one more, we could be working with methanol. We'd be working with something like methanol, which is CH4O. And that would be the alcohol of methane. Excellent. Now what about some aprotic solvents? What kind of solvents might we use in the lab that are aprotic? Well, the first one, it's very commonly used, although it's becoming less common, is dichloromethane. Dichloromethane is commonly used because it's not miscible with water. So it won't mix with water, but most things will dissolve in either one. So if we're not able to pull something out of water, we can shake it around with some dichloromethane. The dichloromethane pulls our material out of the water, and we can pull it out of the dichloromethane. So CH2Cl2. So that looks like this. Another really common solvent that is aprotic is acetone. Acetone. What is acetone's structure? Acetone, C2H6O. And it's actually going to have a ketone bond. So it's C3. So acetone and water are miscible, but acetone doesn't have any polar bond or hydrogen bonds. So it's not going to have hydrogen binding. So it's an aprotic solvent. So that's the next piece of this. We need to be able to differentiate, is it a protic solvent or an aprotic solvent? And whenever you're looking at these, you can always Google, you can always look up what kind of bonds does this have. You should look at a molecule, just type in what is the molecular structure of blank. Simple enough. And then we should be able to see, does it have an H to N or an H to O bond? That'll tell us right away.